Hi, and welcome to today's YouTube video. And what I will be doing is I'll be going through everything that's on the left-hand side of your screen. So we actually have state symbol equation for the production of ammonia in the Haber process. Notice that there is a reversible reaction arrow in there. So not only do you have nitrogen and 3 hydrogen molecules combining together to form 2 ammonia molecules, but at the same time, when the ammonia molecules formed, you find that you get 2 ammonia molecules easily turning back into the nitrogen and the hydrogen. So that's not very helpful, especially if you're trying to synthesize the ammonia. So we'll have a look at that in greater detail. We'll also look at the sources of the hydrogen. Some students actually get stuck on that particular one. They can recall that nitrogen comes from the air. Around roughly 78% of the air is nitrogen, but hydrogen is the one that gets people a little bit stuck. So the source of hydrogen is methane. We'll look at that, and we'll also look at an alternative source of hydrogen that you can quote in your exam as well, to do with cracking. As the typical conditions in the Haber process being 450 degrees centigrade, 20,000 kilopascals, which is another way of stating 200 atmospheres, and an iron catalyst. Again, these 3 simple facts are facts that you'll just have to sadly memorize and make sure that you are able to recall in your exam. But what we'll also do is we'll spend a little more time on being able to explain in terms of rate of reaction and position of the equilibrium when the typical conditions stated are used in the Haber process. My next video will be talking about the contact process, but there's a lot of similarities between the two with regards to safety considerations and general economics. So students find it a little bit difficult to talk about that and explain that extensively, so I'll help you through that. So we're going to talk about the Haber process in particular. The nitrogen source of nitrogen is air, as I've stated. Is roughly 80% of the air is nitrogen, roughly around about. But to be more accurate, it's around about 78 to 79, depending on which part of the world you are. And 20% oxygen. So what you have to do is you actually have to remove the oxygen from the air to enrich the gas mixture with nitrogen. The oxygen is actually removed by burning the oxygen away in the presence of hydrogen. So the hydrogen actually combines with oxygen to form water. It's quite an okay product to have. So removing the oxygen from air leaves mainly nitrogen, a small amount of other gases that are removed in a cleaning process called scrubbing, and as mentioned, the heat given out in this reaction, this very exothermic reaction, is used in the plant itself. The hydrogen is obtained usually by reacting natural gas, so there's a real reliance on a fossil fuel industry and petroleum for the methane, with steam, so that's CH4 reacting with 2H2O, giving you CO2 and 4H2. You do need the presence of a catalyst in order to help that. But you can also help yourself by making hydrogen through the cracking of hydrocarbons. So within your organic lessons, I hope you've learned that a hydrocarbon such as ethane can be cracked using catalyst, and that can then form ethene and H2. So there's the hydrogen that you have formed. You usually use something like porcelain aluminium oxide, zeolites to catalyze that reaction. A catalyst will generally work. Okay, so what is the process? There's a nice big diagram on the left-hand side just to help explain it. So let's assume that you've got your source of nitrogen. You've already reacted it with hydrogen. You've reacted the air with hydrogen to remove the oxygen. If you didn't remove the oxygen, you would actually have an explosion later on in the process. And the nitrogen comes in over here. The gases are mixed, so the nitrogen is mixed with the hydrogen. They're scrubbed, so you actually remove and clean all of the impurities that are there and any unwanted gases that you don't need. And you then pump at pressure through a compressor. You pump the gases so that you rack it up your pressure up to around 200 atmospheres, 450 degrees centigrade is what you need to heat it up to. So these gases are compressed, they are pushed all the way through, and then what happens is they go like a pinball machine, they go through this long convoluted pathway through the converter. Now, you'll notice that there are some beds here. These beds actually contain the catalyst iron, and the catalyst allows you to get to the point of equilibrium, the dynamic equilibrium, as quickly as you can. It doesn't increase the yield of ammonia. It just gets you to a point where you establish the equilibrium and you start forming the ammonia as quickly as possible. It's all about time. So you've got your 200 atmospheres, you've got your 450 degrees Celsius, you've got your iron catalyst, and this long convoluted pathway allows yourself to have maximum contact time with the catalyst so that you form as much ammonia in that opportunity as you can. The equilibrium that is established, if it was allowed to reach equilibrium, would give you roughly around about 30% to 40% yield, but the reaction is not allowed to reach equilibrium. We actually just can't wait. So we, in reality, get around about 15% yield, just getting this all the way through as quickly as we can just to get some ammonia. And the reason why is because what we do is we actually condense the ammonia. If you condense the ammonia, you're actually removing it away from this dynamic equilibrium. So if you reduce the concentration, what you find is that you actually have less backwards reactions taking place because your concentration of ammonia is not so much in the space that you have, in the gas volume that you have. So you have more forward reactions taking place. Your forward reaction rate is then greater than the reverse reaction rate, so the equilibrium is driven over to the right hand side. So the equilibrium shifts to the right hand side until you find that your reactants go down in concentration, your products go up in concentration. That's your desired product, which is ammonia, and the dynamic equilibrium is re-established. So to summarize that particular point, if we cool down the ammonia, the gas mixture, the ammonia actually is the first one that turns it into a liquid, and the ammonia then can be drawn away from the process in the form of liquid ammonia, and you just store it in tanks under pressure. The removal of the ammonia shifts the equilibrium over to the right-hand side because you have more forward reactions than backward reactions at that particular point. So you are forcing your forward reaction rate to increase. That then produces more ammonia. So you increase the yield and you get to a stage where you re-establish your dynamic equilibrium. You're constantly removing your ammonia. So you're constantly pushing your equilibrium over to the right-hand side. Now, that does produce a lot of unused gases. So you've got unused nitrogen, unused hydrogen. It would be a shame to waste those. So what happens then is that they are pumped through and back into the converter. So you have this constant recycling. You have this constant recycling. It goes round and round and round and round and round. Okay, so to summarize, the reactants are nitrogen and hydrogen. The nitrogen is obtained from air, and the hydrogen by reacting natural gas, which is methane, with steam, or by cracking hydrocarbons. The two gases are mixed and scrubbed, which means that they are cleaned to remove impurities. You then compress the gas mixture. More and more gas is pumped in until the pressure reaches 200 atmospheres. The compressed gas then flows to the converter, a round tank with beds of hot iron at 450 degrees centigrade. The iron catalyzes the reversible reaction, but only 15% of the mixture leaving the converter is ammonia. The mixture is cooled until the ammonia condenses to a liquid. the nitrogen and hydrogen are recycled to the converter for another chance to react, and steps 3 and 4 are continually repeated. The ammonia is run into tanks and stored as a liquid under pressure. Okay, so now we're going to move on to being able to explain in terms of rate of reaction and position of the equilibrium where the typical conditions stated are used in the Haber process. The question is, well, why not raise the temperature? Generally speaking, temperature does affect rate of reaction, and generally everything that you've known about in chemistry and you've learned about in chemistry has told you that if you increase the temperature, you increase the reaction rate. Now, there's a little bit of a proviso on this one. The forward reaction is exothermic. So if the forward reaction is exothermic, the reverse reaction is endothermic. If you raise the temperature, you're actually supplying more energy into the mixture, and that will encourage the endothermic process. And the endothermic process is the reverse reaction. So you don't want to form your ammonia and then suddenly find yourself breaking it up completely. You can't ratchet up the temperature. So if we have a look at this graph over here, there are set temperatures that you could actually fix for your reactions. And let's say, for example, let's focus on the 450 degrees centigrade that is chosen for the Haber process. In actual fact, the conditions are the same as the conditions that you can see over here, where I have given the letter Y. Now, 450 degrees centigrade is over here, and this is talking about the yield of ammonia. So at 450 degrees centigrade, at the chosen pressure, which is 200, you'll find that it is almost 30%. It's actually closer to 28% than it is to 27%, which is in the halfway mark on these squares. So you'll get roughly 28% yield of ammonia. Okay, now in our industry, what we want to do is we want to try and maximize that. We want to try and make as much ammonia as we can. But because this reaction is reversible, this yield will never, ever be 100%. And look, if we raise the temperature from 450 degrees centigrade to 500, we actually find that our yield of ammonia actually falls. If our yield of ammonia actually falls, that's not a very good thing. The reason why the yield of ammonia is falling is because raising the temperature is actually encouraging the endothermic stage. Okay, and that is the reverse reaction. So our endothermic stage is what we want to try and restrict. So 450 is there. Now, why can't we choose 400? Why can't we choose 350 degrees centigrade? The reason why is because we are actually using a catalyst. So the catalyst, the thing about a catalyst is that you actually need to make sure that you have a certain temperature that the catalyst can reach in order for it to actually activate. So you can activate your catalyst, but only at a fixed temperature. If you have chosen a temperature that's lower, your catalyst, believe it or not, will not actually work so well. So you may have a higher yield, but the problem is that you may actually find that ammonia forms so slowly that it's just not worth it economically. So what you want to do is you want to have a high yield, but you want to be able to make the ammonia as well in as short a time as possible. So that's talking about the economics behind it. Okay, so that is the reason why we choose 450. It's not too hot. If it's too hot, then your yield will go down, so your process is not economically viable. And if it is too cool, your catalyst will not kick in. Your yield will be high, but it won't be made in the time that you need it to be made. So again, that affects the profitability because you want to try and make it within a set period of time. To improve it, the yield and reach that compromise, you choose 450 degrees centigrade. All right. Okay. So that was a very, very long way of getting around it. Now, what about the pressure? You'll notice that whatever temperature we choose, if you increase the pressure, you actually increase your yield. So a higher pressure always gives you a higher yield. That's why these are all going towards the top right hand side. So it's pretty clear that if you raise your pressure, you are going to make a higher yield. So we raise the pressure, but the problem is if you actually raise it too high, there are some safety conditions. And also, in addition to that, the cost of stronger pumps, the cost of stronger piping and thicker piping to withstand that higher level of pressure, all of those costs taken together will actually mean that you make less profit as a result from this industry. So you do need to have a high enough pressure in order to shift the equilibrium over to the right hand side, because these gases, when they are under pressure, because you have more volumes on the left hand side of gases than you have on the right hand side, when you raise the pressure, you are actually pumping in more nitrogen molecules, more hydrogen molecules, and what you are then finding is that they can react more frequently together. So if you have more nitrogen present, more hydrogen present, your forward reaction rate goes up. It goes higher than your reverse reaction rate. And as you are then making ammonia molecules, they are taking less space up. If they are taking less space up, if you are then trying to inject more nitrogen and hydrogen at the same time, you're literally allowing more hydrogen and nitrogen to come in. That nitrogen and hydrogen has been replaced, and you have a favorable condition. So raising the pressure, if you raise the pressure and constantly raise the pressure while at the same time draw out the ammonia by condensing it, that is actually really, really favorable. And that's the reason why pressure is good for this reaction. So the principle seems to be the case that if you are putting this under pressure, the reaction mixture seems to respond in such a way that it actually tries to reduce the pressure by shifting the equilibrium over to the right hand side. And you can use that aide memoir to help you remember. And that aide memoir was brought up by a fellow called Henri Le Chatelier. So raising the pressure is a good thing. If you raise the pressure, but you can't raise the pressure too much because that becomes too expensive. So to summarize our chosen condition, the highest, as you can see, the highest yield on the graph is at 350 degrees centigrade and at 400 atmospheres. That's all the way up here. That's the highest yield you could actually get. But we don't choose 350 degrees centigrade. We choose 450 degrees centigrade. And we don't choose 400 atmospheres. We choose 200 atmospheres. And the reason why is because at 350 degrees centigrade, the reaction is too slow. 450 degrees centigrade gives a better rate. And secondly, a pressure of 400 atmospheres needs very powerful pumps, very strong and steady pipes and tanks, and a massive amount of electricity. 200 atmospheres, however, is safer and saves money. So the conditions inside the converter do not give the maximum yield, but then the ammonia is removed, so more will form. And the unreacted gases are recycled for another chance to react, so your final yield is actually high. Please, please, please remember that iron speeds up the reaction, but it does not change the yield. It speeds up the reaction in both directions. It helps to get to your dynamic equilibrium in a much shorter time, but it actually aids the bond breaking and the forward reaction as well as the reverse reaction. A quick checkpoint, so you can pause the video and tackle these questions. Ammonia is made from nitrogen and hydrogen. How is the hydrogen and nitrogen obtained? What is the process for making ammonia called? Write an equation for the reaction. And then look at the catalyst beds in the diagram. What is in them and why are they arranged this way? Okay, so pause the video, have a go at those questions. Okay, so before we answer those questions, we need to just make sure that we really complete this by thinking about where you would build an ammonia plant. You'll actually build an ammonia plant pretty much close to a natural gas terminal. Why? Because you need natural gas for your hydrogen. And many petroleum and gas companies now make ammonia as a way to increase their profits. So we wouldn't be surprised if a company like ADNOC would be looking and investing in that company in this industry. So the answers to the questions: well, nitrogen is made and supplied by removing oxygen from the air. Hydrogen is supplied by reacting methane with steam or cracking ethane. The name of the process is the Haber process. The equation for the reaction, now you'll notice that there is a forward reaction. That's actually referring to the production of ammonia. But the equilibrium that's set up would have a double speared arrow. So it would be a half arrow forward and a half arrow backwards. So just be very, very clear as to what it is that the question is actually asking you. The part B question is talking about what is the process for making ammonia called. So it's very, very clear that you're actually referring to the manufacture of ammonia. The catalyst is iron, and the reason why they're arranged this way is to give several chances for the gases to react. Here's another couple of questions for you to now consider. So pause the video, have a go. And before you pause the video, I will quickly go back to the graph. So you can pause the video if you're looking at the questions, but then you can play it for a few more seconds and I will refer back to the graph in those few seconds. So I will come up with the answers now. So high pressure favors the side with fewer molecules, the product. The forward reaction is exothermic, so it's favored by low temperatures, but not too low. You don't want it to be too low. Otherwise, you won't activate your catalyst and your reaction rates will be too low. It would be dangerous and expensive to work at such high temperatures, and at 250 degrees centigrade, the reaction would be too slow. The percentage yield of ammonia is approximately 28. I actually went through this on the video, so if we actually have a look at where Y is, all the way up from 200, so this is 0, 50, 100, 150, 200, so if you go all the way up here, and then drag yourself all the way across, and make sure that when you do this in an exam, you actually do the dotted lines or have a dashed line going exactly where you want to read everything off, and then use a ruler to have a dashed line to go all the way across, so it's just about 28% here. Okay. Right, and the final answer was that they are recycled to give the gases another chance to react. So hopefully you've been through everything that you need to know about being able to explain in terms of the rate of reaction and position of equilibrium when the typical conditions stated are used in the Haber process, including safety considerations and economics. Please, please, please make sure that you use a suitable way of memorizing the facts that you need to state. I would recommend flashcards. If they ask you for the symbol equation for the production of ammonia in the Haber process for Cambridge IGCSE, I would give this equation with the reversible reaction sign. State the sources of hydrogen as methane and state the sources of nitrogen as air in the Haber process, but you can also state the sources of hydrogen as being from the cracking of hydrocarbons. So remember that if you forget that the source of the hydrogen is methane, and state the typical conditions, trying to remember 450 degrees C, 200 atmospheres, and an iron catalyst. Best of luck with your revision and your preparation for your final exams. Take care. Oh, and don't forget to like and subscribe. It really does help support the channel. Bye-bye.